In this video, we're going to quickly and kind of over the top lightly go through everything we've covered in this graph section from Rolle's theorem, the mean value theorem, the graphing and the optimization. We're going to go through that and sort of give you a brief overview as if you were getting ready for a test. And remember that in the description below that there's links to, in this case, not practice problems, but sort of a mini practice test to sit down and see if you can get through the whole thing without any access to any other materials. And if you can't, well, then I guess you're not ready for the test yet. All right. So if you have any trouble with any of these sections, remember there's a full up video on each topic in the previous videos. So go back, and each one has between 30 to 55 minutes on each topic, and then you can dust that off if you've forgotten one of them, or if you've looked onto this video for the first thing, then each one of the topics we're going to cover today has a previous video expanded. Just go back, which also have practice problems. Just go and look at the playlist and follow back, or just follow the previous links that are in the description. Okay, let's start off with Rolle's theorem. And Rolle's theorem says, let f be a function that satisfies the following hypotheses. F is continuous on the closed interval, f is differentiable on the open interval, and f of a is equal to f of b. Remember, that means the two y's of the two endpoints are equal. Then there is at least one number c in that interval such that f prime of c is 0. Now let's talk for just a second. Let's pretend that you're getting ready for a test. Some teachers are going to say something like, here's a function, here's a interval. Make sure that this satisfies Rolle's theorem, and then find c. Well, do you know what these three things are that you have to prove before you can dive in and get busy? You have to prove that it's continuous, which may need some explanation on your part. You have to say it's differentiable on that interval, and you have to show that these two y values, f of a and f of b, are equal. So be sure that you don't just memorize, oh, I know how to find c. Okay, because we've been doing that for a while. We've used this principle that there's some place in there perhaps where the slope is 0 on the graphing and on the optimization. So we've used this last part quite a bit. But if you don't know this part and your teacher says to justify why you can use Rolle's theorem, if you don't do that, you may get no credit at all. Okay, so be sure you can do that. So let's say that what we're going to have is some function. I decided to go for trig 2 sine 3x. I could make that look like a sine. There we go. Now, so there's my function, and I am curious about the interval from pi over 6 to 5 pi over 6. Okay, now, so the first thing I would need to do is to talk about whether it's continuous or not, and yes, it is. F of x is continuous. And the reason we know that is because sine itself is continuous from negative infinity to infinity, right? Because we know what sine does. All right, there's no asymptotes, there's no domain restrictions. We also know that it is differentiable because there's no points on it where I can't take the derivative. Now, it's continuous. Okay, so let me back up to the one I just did. It's continuous on negative infinity to infinity, which includes this given stated interval. I would have accepted that negative infinity to infinity because it includes that interval, like I just said. Some teachers may not, so you may need to be absolutely sure. So what you could do is to say, since f of x is continuous from negative infinity to infinity, it would be then obviously continuous on the given interval, right? So you could just make kind of a more complex sentence and kind of fulfill that thought. So be sure that if your teacher's the kind that's, and there's nothing, I'm not saying that there's wrong with them. Okay, but every teacher has the parts where they're a little bit more flexible and where they're a little bit more committed to an exact answer. Some teachers are like, has to be exact all the way through, which is actually excellent training. So you could say something like, since, you know, f of x is continuous from negative infinity to infinity, it is continuous on pi over 6 to 5 pi over 6. This is where y'all um, getting familiar with what you're and paying attention to what your teacher says, whether it's on video or in class. If what they're saying is something along these lines, you need to verify to them that you are absorbing what they're saying by phrasing it back to them in the same way. It always kills me that students are like, well, I know my English teacher is picky. And I'm like, well, so am I. I'm just not picky about this particular one, but there's other things I'm really picky about. All right. Everybody has their thing. So f of x is differentiable. I don't know how you want to explain that. Let's talk about f of a and f of b. So f of pi over 6 would be 2 sine 3 times pi over 6. And if you remember your trig, you may be going, these ones with multiple, the 3x as opposed to just x. All right, maybe having you kind of roll your eyes. So the 3 cancels into 6 and you have pi over 2. So it's 2 and sine of pi over 2 is 1. So this is 2. Now, one of the things that I am extremely picky about, and if any of my former students are seeing this, they're probably going, oh, she's lost her mind, is I don't let them double column. But so you can see it right here on the screen together. I'm going to do that. Whereas your teacher may be going, oh, that's just fine. I would have been saying, absolutely not. All right. So this is 2 sine, 3 goes into 6 again, 5 pi over 2. And so this is 2 times 1. So this is 2 as well. So you can see that, yes, this is the third step. And you can see that f of pi over 6 is equal to f of 5 pi over 6, which I would also want to see you have actually written out as opposed to just leaving it there. Okay, now that we've got this proven, we think, according to Rolle's theorem, that there could very likely be at least one, if not more than one. So we're going to take the derivative, I should get up there where you can see it, of f. So f was 2 sine 3x, so it's 2. The derivative of sine is cosine. Leave the inside alone, loop back in, and take the derivative of the inside. So this is 6 cosine 3x. Now, what we're looking for is these critical numbers where either the numerator is equal to 0 or the denominator is undefined. This is the numerator is equal to 0 when we've gone through and done all the minimum and the maximum and the optimization and everything. So we're looking for where this is equal to 0. So we're saying 3x is equal to the inverse cosine of 0. And remember that cosine repeats every 2 pi. Okay, that's its period, where k is an integer. Now, where is cosine equal to 0? It's equal to 0 at pi over 2. And I'm going to double column again. And 3 pi over 2. So let's divide everybody by 3. Remember, you divide all the way across. So you've got pi over 6, 2 pi over 3 now. and 3 pi over 6, which is actually pi over 2, right? Plus 2 pi over 3. Okay. Okay. So where k is an integer. All right. So what if k is 0? Then if k is 0, x is just pi over 6. If k is 1, so this is one that I want to consider. If k is 1, x is pi over 6 plus 1 times 2 pi over 3. So this is 5 pi over 6. And these are our endpoints of our interval. And let's go over here. If k is 0, x is pi over 2. And if k is 1, x is pi over 2 plus 1 of the 2 pi over 3's, because k is 1, which is 3 pi over 6 plus 4 pi over 6. So this is 7 pi over 6. But this is outside our interval. So we need to exclude that. Okay? So let's go back up here. And do you see, let's go back up here to this statement. And it says, then there is at least one number c in the open interval, okay, such that the derivative is equal to 0. So the open interval does not actually include the endpoints. So even though these give me 0, right, pi over 6, they're the endpoints, and we want between pi over 6 and 5 pi, so the only one we have is c is pi over 2. Okay? And I graphed this. And here's your two endpoints, pi over 6, 5 pi over 6, and here's the pi over 2 down here. Okay? So far, so good? All right, on to the mean value theorem. So the mean value theorem says, let f be a function that satisfies the following hypotheses. First, it's continuous on the closed interval, it's differentiable on the open interval, and there is at least one number c in the open interval such that the derivative is equal to the slope. Remember that this is the slope using calculus, where you get essentially a function description, a formula, equation for the function at any point on the curve, and this is the slope in your college algebra approach. And what they're saying is there's some point on the graph where these two things are equal. Makes sense? Okay. So keep again, keep in mind again that if your teacher just says, show that this meets the mean value theorem criteria, and then they give you some sort of a function to analyze, that you're going to have to be sure and state that it's continuous and it's differentiable. So let's say that we have this function, which is x cubed minus 8x squared, which is a polynomial. And I'm curious about what's going on between -1 and 2. So 1, I would have to say f of x is continuous from -infinity to infinity because it's a polynomial. And so continuous on -1 to 2. Now, it's also differentiable because I don't have any portions on it on a polynomial that have those sharp turns, cusps, or asymptotes or anything where I can't take the derivative. Okay, and here we go. All right, so I need to compare the slope from college algebra to the slope from calculus. Okay, so the slope from calculus is the derivative function, 3x squared minus 16x. Okay, from college algebra, I need to come up with my ordered pairs. All right, so f of -1 is -1 cubed minus 8 times -1 squared, because we're using the original function because we want a point on the original line. Okay, so this point is -1, -9, and f of 2 is 2 cubed minus 8 times 2 squared. So this turns out to be -24, and this point is 2, excuse me, -24. So calculating up the slope, you'd have -24 minus a -9 over 2 minus a -1 or -1, however you want to say it. So this turns out to be -15 over 3, which is -5. Okay, so what the mean value theorem says is there should be some place on the curve that has the slope. So here we go. Let's solve it. And you would say, well, let's see if we can factor it. And it looks like it does. So x would be 1/3 and x would be 5. Okay, but remember our interval was -1 to 2. So this one's outside our interval. So, teachers do that sometimes. Sometimes it's just because the problem gets made up and it happens and they think, oh, that's cool. Let's see if the students recognize it's outside the interval. So don't give them an extra one they didn't ask for. Okay, so the only thing I have is that C is 1/3. Now, when you get problems like this or you make up problems like this, then what you have to do is make sure with any sort of reasonable certainty that the problem actually worked or that you did your answer key right. So what I actually did is this was not part of the problem statement, but I actually went and calculated up the secant line equation, and that would be the line between the 2 points on the endpoints. Okay, so I use this one because I thought the math would be easier. So y turned out to be -5x minus 14. And then for the tangent, so see, these two should be parallel. Okay, the secant line, these 2 points here form the secant line, right? And the tangent line is the one that belongs with this C, all right? So we have x is 1/3. Now you have to go back to the original function, not the derivative, to calculate up the point on the curve. If you want a point on the curve, you always go back to the original function, not the derivative. Okay? So when I clean this all up and got a common denominator, sometimes I don't know if me going through all these steps helps y'all or not. It's what I actually do. All right, so it's not going to hurt you. You can just skip forward. And for those of you who are tired and trying to do this after work or after a long day at school or a long day of taking care of your obligations, sometimes having all these little steps helps. I hope. Alrighty, we are there. Okay, so this is the tangent line. This is the secant line. There it is. Okay, so this curve right here, I missed it. There it is. Way down there. Somewhere. Okay, this is the actual main curve. Because there's a lot of blue going on there. All right, and here's your tangent and your secant curve going through those points. So see how they're parallel? That makes me feel better. Made me feel better. I was going, all right. Now, there's 3 separate videos on how to do everything you never knew you wanted to do about graphing. So there's one for polynomials, one for rational functions, and a separate one for trig functions. If this is, you just stumbled onto this, you might want to go back and look at those. You can go use in the description, use the previous videos and just back up, or you can look at the playlist. But I decided the best one for us to do a review would be kind of a more straightforward rational function one. So we are going to start off with that. I just want to make sure my graph was there. And this is a list that my students made up after having watched me do one of these problems on the board with them. And so I always have them come up with their list, and this is the of all the steps that we did so that they could have this for their test. I do provide this because I want to see all of these details in exactly this order, and so that because it's hard to grade this test if you have this much detail. So this is where this came from. I think they did a great job every semester because they'd made it up their own every semester. Okay, here we go. So the domain, remember the domain starts off with all real numbers unless you have variables in the denominator, square roots. Now we know there's other things that have problems and asymptotes like the logarithm functions and stuff like that. But for the traditional rational functions, we're looking for variables in the denominator, square roots in there somewhere. Okay, so I've got variables in the denominator, and I can't have 0 down there, so x can't be 4. If you tell your teacher x can't be 4, you're telling them what the domain can't be, and what they're asking for is what the domain is. Don't tell me what it's not. Tell me what it is. So what it is everything else but that. So this is the domain. Then we have our x-intercepts, and again, in the longer videos, I explained to you that I had a student who told me they knew which one they were doing with the x and y intercepts by whether I put an s on there or not. So they both have possible s, meaning there could be more than one, but you should know by now that if you have a y-intercept and it is a function, you can't have two y-intercepts because they'd be one over each other and it would fail the vertical line test. Okay, so it could be more than one x-intercept, but there should be only one y-intercept if it has that. Okay, so to find an x-intercept, you set y to be 0, which is this whole function, but if you're going to get 0, you get it out of the numerator because 0 out of the denominator is undefined. So all you really need is the numerator. But depending on your teacher and you and what keeps you sane, okay, I would suggest you start off with the original function. But if you like starting off with the numerator, that's okay. Now, some teachers will let you say x is negative 1/2. I am not one. I would want to see an ordered pair. So one of these two answers will make your teacher happy and one will probably not. Or, well, let me rephrase that. Either way, your teacher's happy with this one. Okay, if it's an ordered pair, they're really happy. Okay, because if they anticipated just x is equal to negative 1/2 and you gave them an ordered pair, they might actually give you a little bit extra credit. Okay, because you got a point. All right, but if they wanted the point and you didn't do that, you're going to have points taken off. Better safe than sorry. So one of the things I hope to do in these videos is to help you improve your skills as a student, listening to your teacher, watching out for the details and how to study and how to kind of know what to look for. Because a lot of students up until Calc 1 have never actually had to study math, so they don't really know how to do that. It's always just been absorbed. And now sometimes it's a work in progress. All right, so for y-intercept, you make x 0, get an ordered pair. Let's talk about symmetry, just in case they ask. So for symmetry, you would replace x with a negative x and see what you get. If you get an exact match to the original function, if it's an exact match, okay, so all the new negative signs clean up and you get an exact match. Okay, so an exact match to the original function is considered even, and that's symmetric with respect to the y-axis. If it's a true opposite, every sign in this new version is the opposite of the original version, then it's odd, and that's symmetric with respect to the origin. Odd. Okay, so remember the original function was 2x plus 1 over x minus 4. So this is minus 2x, which is the opposite, plus 1 is not the opposite, minus x, which is the opposite, minus 4, which is not the opposite. So everybody has to be an opposite, not just the ones you stuck negative x in. So since it's neither exact match, nor is everybody an opposite, then it's neither even nor odd. So there is no symmetry. Okay? And for periodicity, we're looking at things like trig functions, but there is none. And vertical asymptotes. And if you have a vertical asymptote, I'm expecting you to talk about the limit on either side. And we knew we had a vertical asymptote because I have a non-removable discontinuity at x is equal to 4. So let's talk about the limit as x approaches 4 from the left. So you would get a positive number out of the top, and 4 from the left is something like 3.999. So if you have 3.999 minus 4, you have a tiny negative. And as we discussed in great detail in the limits section, you don't really need values, but if you know you have a positive something divided by a wee little tiny negative number, you have a negative huge number. So this is negative infinity. Okay, so then if we're going to do the limit as x approaches 4 from the right, and 4 from the right is something like 4.001, really close, then you would have a positive number on the top, and then you would have 4.001 minus 4 is a wee little tiny positive number, and a positive number divided by a wee little tiny positive number is a positive huge number. And you need to thank your teacher if they require you to make a complete sentence instead of just boxing in infinity or something like that. Okay. Because it's good practice. You're going to go into some sort of a profession where you need to be a professional in your ability to convey information. So this is good practice. Excellent practice. Be sure and thank them, okay, for being picky like that. Then we're going to talk about whether it's got horizontal asymptotes. Using limits. So we're going to take the limit as x goes off to positive infinity up to x plus 1 over x minus 4. And the technique you learned back in the limits videos in the limits section of your book was you divide everybody in the top and bottom of this fraction by the biggest powered term in the bottom. And the biggest powered variable term in the bottom is just your x. And then you reduce. So 2x over x is 2. 1 over x doesn't reduce. X over x is 1 minus 4 over x. Okay. Now, just like some positive number divided by a wee little tiny number gets you some sort of a huge number, then 1 divided by a huge number like a billion, 1 over a billion, 1 over a million, that's close enough to 0 for pretty much anything. 1 over a million is really, let's say it's 0. And then 4 over that same huge number is also 0, so this reduces to 2. Okay? And just to make sure it's the same on the other end, got stuck there for a second looking up there at the infinities. We're going to do the same thing. We're going to divide by the biggest variable power in the bottom. Divide everybody, whether they're a variable or not. Reduce. So you have 2 plus 1 over x over 1 minus 4 over x. And even though this is going off to like negative a billion and negative 1 million, 1 divided by negative a million is still 0. So this is 2. Now you may be remembering that in college algebra there was a series of possibilities that you may have memorized that told you this was 2 a long time ago. I don't know why I keep refusing to write that negative. There we go. But we are now exploring the calculus way to get there. All right, then we're going to talk about the first derivative. And I'm going to write down the original function so you can actually see it. And so this is the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So when you clean this up, okay, I just saw something I'd written down incorrectly on my notes, and glad I didn't say that. Okay, all right. Somehow I decided all my 4's needed to be a 1. All right, so that was the first derivative. Excuse me. So then we're going to use the first derivative to talk about or try to explore critical areas, critical points, values, whatever you want to call them, and using a sign chart. Different teachers have different ways to analyze this. So what we're looking for is where the numerator is equal to 0 and where the denominator is equal to 0, because that's where it's undefined. All right, well, -9 can't be 0, so that's out for a possibility. And x minus 4 could be 0 and x is 4. So my little sign chart's going to only have a 4 right there. Now keep in mind that what we're working with is -9 over x minus 4 squared. And we would normally pick a number to the left and a number to the right for test points. And you'd have a little test point. And you would talk about your signs. And you would decide whether it's positive or negative. But in this case, it's really kind of trivial because, look, the top is a -9, so it's always going to be a negative because you're not substituting any other value in there. And no matter what x is, after you subtract 4, even if it is negative, after you square it, it's going to be positive. So it's always going to be a negative divided by a positive, so these are always negative. Okay? So this is decreasing and this is decreasing. All right, so next question. Where is it increasing? It isn't. There are no places. Some people say in a, in a, not possible, whatever, decreasing. And so it's decreasing to the left of 4 and to the right of 4. Some students want to try to say negative infinity to infinity, but y'all, keep up with this. At 4 is an asymptote, right? So the whole graph breaks and has a vertical asymptote there. So it is not decreasing through an asymptote. Okay, there's a wall there. So it would look like this. Okay, so L is next. So a minimum, absolute, or local. Now, we didn't have any little, remember when we did the sign chart? If we had done a sign chart and it had like something like this, and this was not an asymptote, okay? If it actually had a point that went through there, we would say, okay, that's a minimum, but we didn't have that situation. So there are none. And then the maximum. We would have been looking for some sort of increasing, decreasing, where you could see like a peak or a mountaintop, and there were none of those either. So let's move on to the second derivative, which will talk about concavity. Remember, the first derivative talks about increasing and decreasing max and mins. Second derivative talks about concavity. So the first derivative was minus 9 over x minus 4 squared. Okay, so to get the second derivative, it's the bottom times the derivative of the top, and the derivative of negative 9 is 0, minus, be careful here, minus the top, which is another negative, times the derivative of the bottom. Bring the 2 down, leave the inside alone, take 1 off the power, loop back in and take the derivative of the inside. And this would be x minus 4 squared again. And I see students who sometimes go, they see the square and then lose track of what they're doing for a moment and forget to square it again because they just see the square. So when you clean this up, you get 18 times x minus 4 over x minus 4 to the fourth. And those two x minus 4s, right, are in common. So you would have 18 over x minus 4 cubed. All right. Then we have the second derivative. Critical values, points, areas, whatever your book and teacher call it, and the sign chart. Okay. So remember, we look at where the numerator is equal to 0 and where the denominator is undefined, which is where it's equal to 0. All right, so 18 can't be 0, so that's not going to contribute. X minus 4 could be 0, so my point I need to check on either side is 4, just like before. Now in this case, I don't have a positive or a negative over a square. There's a cube down here, so it can change signs, right? So the top is always going to be positive, but the bottom, it depends on where you're at, okay? So for my test, let's say x is 3, so I'm looking over there. Then I would have for my signs a positive, and we would go, okay, 3 minus 4 is negative, and negative cubed is negative, so this is negative. So this is going to be concave down. And if x is 4, we already know that the top is positive, not 4. 4 is let's say 5. Let's go on to the right. X is 5. So 5 minus 4 is positive. Positive cubed is still positive, so this is positive. So this is concave up. Okay. So where is it concave up? From 4 to infinity. Where is it concave down? From negative infinity to 4. So remember, we're always looking to see where it flips. And if it does, so if it went from concave up to concave up, there's no inflection points. If it goes concave up to concave down, there's a potential of one. So let's talk about this for a second, because this went down to up. So some students will try to tell me there's an inflection point at 4. But y'all, let's keep our minds on task. 4 is a vertical asymptote. It is an excluded number. There is a brick wall right there, okay? There is not an inflection point there. It's just separated on either side the way it's curving. So this is none. It's really easy sometimes when these are so many details to lose track of what you're doing. So that's a very real concern, because if you look at this sign chart, it 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 just begs you to say there's an inflection point right here at 4. I mean, really, isn't it just almost beyond tempting? So you just have to keep telling yourself, wait a minute, if I'm going to do that, this is one of the reasons I make them do points, okay, is if you went to the original function, because you got distracted for a minute, or you just sort of, you're tired, who knows, and you had said, oh, okay, I think there's an inflection point at 4. When you try to find the y value for, for what, right? What's the point? Then you would have gone, oh, I can't have 4. That gives me 0 down here. So this is, oh, yeah, that's right. There's a vertical asymptote there. Okay. So coming back with points is actually beneficial for you. And this is, if I can find it, way up here. That's how long this problem takes. All right. This is the actual function. Okay. And I had it draw in the horizontal asymptotes and the vertical asymptote. So you can see that it's concave down on this side. So it's concave down and decreasing. And this is concave up and increasing. Okay. Or did I say increasing and decreasing? If I said increasing, I'm terribly sorry. All right. Now, your absolute favorite. Okay. One of the favorite questions that they always ask about optimization is to make this open top box out of a flat piece of cardboard. And part of me appreciates the math that goes with it, but part of me is like, I don't really want a box that's like that, because when you get it flipped up, right, it's not a very sturdy box. So I decided to put my own personal opinion in here. So here we go. You have a piece of cardboard measuring 2 feet by 4 feet. You wish to create an open top storage container for toys by cutting equal size squares from each corner and folding up the edges, and then using, this is me, duct tape to hold the edges closed. Because really, you've just got these edges that just touch. They don't overlap. You can't glue them together or whatever. So we're going to try duct tape. Not the sturdiest container, but it will work for light use. Very light. In other words, just set it there and throw stuff in it, but don't carry it around. Duct tape will help. What size squares should you cut from each corner, and what will the dimensions of the box be if you want the largest volume possible? Okay, so what you have is this box, and it is 2 feet by 4 feet. And what they want you to do is to come in here and cut off a square from each corner. And then what that would do is leave you something that kind of looks like, I'm going to try to get this done. That's kind of bad. And then you would fold this slip up, fold this up, this up, this up, and you would have, and this would be the bottom of your box, and these would be the sides. So these parts are going to fold up and make a box, which again, the edges just come together like this. So to try to hold them together, I guess you'd be looking at duct tape. All right, now, so, and the goal here is to maximize the volume. So the volume is the length times the width times the height. And they want you to cut a square off of each end. So this would be x by x, because we don't know how big we want it to be. So let's just call it x. Now, there are limits, okay, on what the value of x can be. It's not like you could cut off 8 inches off each end or something, because if you look at it and extend x as big as possible, it would extend all the way to the middle. And then what would happen is this whole edge would be, this whole edge right here would be just sliced off and removed, and you wouldn't have that little lip on this side here to fold up. So you can't have X go all the way to the middle, and it can't extend past the middle because then that would be extending, well, it's not physically possible, okay, to cut both sides off and extend into the other side if you've already cut it off. All right. So how big can X possibly be? I guess they would meet in the middle if they were each 1, but that wouldn't give you a box, okay? And it could be 0, but then you would just still have your flat piece of cardboard. So X is somewhere between 0 and 1 because of this. And we use 1 because 4, if you used 4, half of 4 is 2, and you can't get a corner of 2 foot by 2 foot off of something that's only 2 foot long on its own. Okay, so here we go. Now, a lot of times, and there's a whole video on this optimization, you have 2 separate equations and you just substitute one of them into the other, keeping the one you want to maximize or minimize. In this case, this is just a setup for geometry, and so we should be able to kind of write it down pretty easily, right? The way it is. Okay, so what we know right now is that when we take this part right here and fold it up, this is also X, right? By X that you cut out. So it's going to be X tall. The side's going to fold up and be X tall. So the height is X. Okay? So H is going to be X. Now, when you cut, you have 2 feet and you cut an X off each end, then this dimension right here, okay, is the 2 feet I started with minus the 2 X's that I cut off, right? And this dimension right here is the 4 feet that I started with minus the 2 X's that I cut off. Does that make sense? So it'd be 4 minus 2x times 2 minus 2x times x. And I'm always looking for ways to make my life a little easier as far as multiplying goes. So you don't have to, but I'm going to factor out all these 2's and everything. So I'd have 4 times 2 minus x times 1 minus x times x. So this is 4 times 2 minus x minus x squared. 4 times 2x minus 2x squared minus x squared plus x cubed. So I want mine to look a little bit better. And I'm going to take the derivative of it, so I want it to be as clean as possible, so that makes my taking the derivative a little easier. So we leave the 4, and we take the derivative of this 3x, this x cubed and everything, so it's 3x squared minus 6x plus 2. Now 4 can't be 0 because we're looking for where this is equal to 0, because that would be where I need to look to see if there is a maximum or minimum there. But it doesn't factor, okay? Because I can't think of anything that would multiply to 2 and get you to add up to 6, okay? So just because it doesn't factor doesn't mean you get to stop. So what we're going to do is to use 3x squared minus 6x plus 2 equal to 0, because 4 can't be 0, right? 4 cannot be 0. And we're going to run it on the quadratic formula. So here we go. All right. So this turns out to be 6 plus or minus the square root of 36 minus 24 over 6. So it's 6 plus or minus the square root of 12 over 6. 6 plus or minus 2 square roots of 3, because 4 is in there, right? 4 times 3 is what we're cleaning up. And we can cancel out a 2. And there are teachers, one of which worked for me for a long period of time, who I just adored, who would harass me every time I say cancel. Okay. So if your teacher's like that, be careful. I have to tell you, when I substituted in her class, I never used the word cancel. That's for sure. All right. So when you run this on your calculator, these are your two possibilities. Okay. But remember, we had said that we have to restrict x to between 0 and 1, because otherwise we either don't have a box, or we have something we trimmed down and lost the little turned up pieces on each edge. So we had to be between 0 and 1. So this one is outside of our interval. Okay. So then let's just round it off to 2. Decimal places. I'm not even sure that if I had a piece of cardboard, I could be that exact, but we're going to round it off to 2, right? So then this would be the height of the little ears, right? The little ear part that's going to fold up. And then 4 minus 2x would be 3.16, and 2 minus 2x would be 1.16 feet. So the dimensions are 1.16 feet by 3.16 feet by 0.42 feet. And the other thing they wanted to know was the volume, and when you multiply this all up, you get, I don't know, did I actually calculate up what the volume was? I don't think so. So let me do that really quickly. All right. And that would be 1.5395 or 1.54 cubic feet. Yeah, I had to double check that. That's what I typed in. Not a very big box, but we lost a lot when we cut those edges off. All right. Now, so that should take care of a very quick overview. Don't forget to look back at the other videos if you need a more in-depth refresher. There should be a practice little test attached here with solutions for you to do this. And the next group of videos is going to be over integration, which is one of my favorite things. All right. So don't forget to like and subscribe, and I will see you at the next video.